Hi viewers, this is Sri Ramulu, DL in Physics. Today topic is a line spectra of hydrogen atom, right? So now let me enter. See the line spectra of hydrogen atom. So this is the diagrams and having the different series. So generally it is called a Lyman series, Balmer series. See here, it is a Lyman series, Balmer series, Passion series, Bracket series, and finally is a Pfund series. So these series are named under the name of the scientist and where the transition is ending. See here the transition different from different. It is these are the orbits. So electrons are coming, or the electrons are jumping from higher energy level to a lower energy level. So these are the energy levels. So electrons, when the electrons are jumping from different energy levels to the n1 levels, then they forms a series, that is a Lyman series, right? So here the transition occurring, so from this, and see here one example is it is let it is n5. So from n5 to where n1, so electrons are coming from n5 to n1, then they release a wave or a radiations. That radiations contain one type of wavelength. And suppose the electron is coming from the n4 to n1, then also they release one wave. Its wavelength is different than this wavelength. So wavelengths are different. So these wavelengths forms a spectrum. So that is a line spectrum of hydrogen. Why? Because it is with happening with the it is forming because of hydrogen only. So that is why it is called line spectra of hydrogen atom. So here hydrogen atom. All right, and next let me enter. See here, line spectra of hydrogen atom. So the first point, see, it has been shown that the energy of outer orbit is greater than the energy of inner ones. So that is everybody know, as we move away from the nucleus, orbital energy gradually increases, or energy of the orbit increases. And the second point is, when the hydrogen atom is subjected to the external energy, the electron jumps from lower energy state to higher energy state. The hydrogen atom is excited. So here see, suppose it is a nucleus. Around the nucleus many orbits present like this. Suppose electron is coming from, it is higher energy, it is lower energy. So electron is coming from higher energy state to lower energy state, then they release energy. So then this type of atom is called atom is excited. So this atom is excited. So we have to say simply it is atom is excited, right? And next, the excited, third point, the excited state is not stable. Here it is not stable, right? So excited state is not stable. So excited state is not stable. Why? Because the electron cannot stay in higher excited state for long time, right? So how much time it takes? Just 10 power of minus 8 seconds only. So that is why the excited state is not stable. The electron returns to its ground state about at what time? 10 power of minus 8 seconds. So that is the meaning. And the next, this point is, see, the excess of energy is now radiated. So when the electron jumps from the higher level to lower energy level, then energy will really radiate. That is the meaning. So this excess energy is now radiated in the form of radiations of different wavelengths. So these are called spectral terms. So spectral lines, spectral series we call, right? And the next point is, the different wavelengths constitute spectral series. See, spectral series, which are characteristics of atom emitting them. So which atom is emitting? So that is that atom characteristics only we call it is. And the wavelength, last point, the wavelength of different members of only single of here, different members of the series can be found from the following relations. So what I'm saying just now, so let it is a ground state and electron is coming from the higher energy level to lower energy level, then electrons, what happens, they release energy, and they have wavelength. So its wavelength can be found by the following formula. With this formula only we found, right? And next, see here, here it is appearing. See this side here. See, electrons are jumping from different states, different energy levels to the only n1. So ending point of all the electron is n1. Then what happens? This one can release a energy, and second one can release, and third one can release, and fourth one can release, fifth one can release, sixth one, and so on. So these all the electrons which are coming to the n1 state, then they release energy. Those energy may have the different wavelengths, right? And these wavelengths are we call members also. So how can we calculate those energies? See here, so there is a equation, so just now I have shown. By using that relation only we calculate. And here n1 and n2 are the two integers. These two are the integers only, right? And see here the formula, previous formula. What is the previous formula? One new bar, it is a new bar. See, it is a new bar. New bar is equals to 1 by lambda is equals to r into 1 by n1 square and n2 square. What is n1? N1 is where the lines are stopping, right? And one condition is there, n1 is always less than n2. So n1 term is always less than n2, but n1 term is fixed for spectral series. So for Lyman series its value is single, its value is 1, and for Balmer series its value is 2, but its value changes, right? Now let me come back. Lyman series, what is the Lyman series? When we call Lyman series, see the definition of the Lyman series. See, this series consists of all wavelengths which are emitted when the electron jumps from the outer orbits to the first orbit. That is, electronic jumps to the K shell only. See, it is a n1 is equals to n1 is equals to 1 means, see, n is equals to 1 means it is a K shell, right? And here the see, from different orbits electrons are coming, and they are jumping on the n1 or into the K shell, right? So K shell, outer orbit, different outer orbits. And now it is electronic jumping. Generally we call it is electronic jumping. Okay, hence here n1, here the ending point is what? N1 term is 1, and n2 terms, so that means electrons are coming from second state, third state, fourth state, so on up to infinity states only. Suppose if we substitute n1 is equals to 1 and n2 is equals to 2 in the last I have shown the formula, then how much we get wavelength? That is, let me calculate. So 1 by lambda is equals to r into 1 by 1 square minus 1 by 2 square. So here n1, in the place of n1 I have substituted like this, and by simplifying this formula we get 3r by 4. So 1 by lambda is equals to 3r by 4. Then lambda is equals to how much? 4 by 3r. So reverse it, so then you get this one. And next, lambda is equals to 4 by 3 into r value. R is the Rydberg constant, its value is 10.97 into 10 to the power 10 to the power plus 6 only meters inverse. Its unit, meters inverse. So like this, this is the formula, and if we substitute, then finally how much, what we get? 1216 angstrom. So here 1 angstrom is how much? 1 angstrom. 1 angstrom is equals to 10 to the power minus 10 to the power of minus 10 meter. So 10 to the power of minus 10 meter can be taken as 1 angstrom only. So that is here the formula. We have, by substituting, by calculating this, we get this one. So this is called the first member, right? It is called first member. In the first members we got lambda wavelength as lambda is equals to 1216 angstrom. So that means, what is the meaning when we get this wavelength? When electron is coming from n2 to here, from this to here. So yeah, so here second state to first state, ground state. So electron jumps from second state to ground state, then only how much they have the wavelength, this much of wavelength. It is called first member. So like this we have to calculate second member, and no need to calculate third member directly. We have to calculate final, last means that is what, infinity. Okay, so for not only for the Lyman series, for all the series, so we have to calculate like this. And a Lyman series is what? Once again, Lyman series is when the electronic jumps takes place from different outer orbits to K shell, different outer orbits to K shell, that is called Lyman series. Lyman series. Next, second member. And see here, second member means here n1 is 1 only. Always you have to substitute in the Lyman series. N1 is always is equals to 1 only. But n2 value changes. If it is n2 value is 2, it is the first member. If it is 3, that is a second member. If it is 4, that is a third member. If it is infinity, that is the last member. Okay, like this only. So here substituting n1 value and n2 value in this formula, then we get this one. And lambda is equals to 9 by r. Already I have told you the lambda value is this much, 10.97 into 10 to the power of 6 meter. It is a meter inverse only, right? And then lambda value is 1026 angstrom. Next, limiting member. See here, limiting means it is the last. n2 value is how much at this point? Infinity. So no need to calculate for n is equals to 4, n is equals to 5. We cannot calculate all the values. So first and second we have to calculate, and then third, for the third time, so the n2 value substitute directly infinity, then how much we get, we can calculate. Now see here, by substituting infinity value in the place of, it is n1, in the place of n1, in the place of n2 infinity, in the place of n1 always 1 only. For Lyman series only, n1 in the place of n1, 1 is for Lyman series. So 1 indicates Lyman series, 2 indicates Balmer series, like this, for n1 only. And lambda value, by substituting this value 1 by infinity, already we know the 1 by infinity is how much? 1 by infinity is always 0. Something by infinity is 0. Something means that is a 2 or 3 or 4 or 1. By infinity is always 0. So substituting this here 0, then we get 1 by 1 square is 1 only. So r, simply we get r. So but 1 by lambda is r, means lambda is equals to 1 by r, and we get 912 angstrom. And this series, so that means which are coming the waves outside. See, this series is Lyman series may be appeared in ultraviolet regions only. If you observe the electromagnetic spectrum, in the electromagnetic spectrum, Lyman series can be found in where? Ultraviolet region only. All right. And next, see here, for Lyman series n1 value is 1, and here also n1 value is here also n1 value is 1, and here also 1, but n2 values changes. Okay. And next, Balmer series. For the Balmer series is what? Balmer series, this series consists of all the wavelengths which are emitted when electronic jumps from the outer orbit to the second orbit. Second orbit means that is L shell. Okay. So here n1 is what? Second. And in Lyman series n1 is what? 1. In Balmer series n1 is 2, second one. Okay. So here electronic jumping is from where to where? From different orbit to different shells to different orbit to where? Into the n2 only. Their ending point in the Balmer series is n2 only. So we have to calculate. Suppose electronic jumping is taking place from third shell to second shell. Then what is the wavelength of emitted radiations? So for this, n1 is substitute 2, and the place of n2 is 3. So substituting the formula, then we get this one by simplifying. We get a wavelength which are emitting when the electron jumps from third state to second state with this much of value, 6563 angstrom. So value is wavelength is increased in the Balmer series. And it is the first member. Second member is what? See, second member. In the second member, n1 is always 2 only, but n2 value changes. In the first member, n2 value is 3 substituted. In the second member, n2 value is 4. In Balmer series, it is in Balmer series. And substitute these values here, then you get what value? Lambda value. Its value is a 4861 angstrom. Next, limiting. Limiting means n2 value must be infinity. Then only it is called limiting. And n1 value is fixed for Balmer series, that is 2. And for it is the last term. Infinity is the last one. Already we know the something by here. The something by infinity is how much? 0. But here 1 by 2 square is 4, r by 4. But here lambda is equals 4 by r. 4 by r value is substituted. And this series, where we see this series, it is also in seen in ultraviolet region. Which one? Balmer series also. Balmer series and Lyman series, both series. Next, after Balmer, which series is there? Passion series. Passion series is what? Electronic jumping. Where to where here? Electronic jumping to third state. Third. That means n1 value is 3 now. Right? So, more than 3. See, n1 value is 3. So, the electronic jumping takes place from 4, 5, 6, and so on, like this. Okay. So, the electronic jumping takes place in this manner. And now substituting these values, let me select first n1 is how much? N1 is 3. And take first n2 is 4. If it is n2 is 4 in the Passion series, that is the first member. If it is n2 is 5 in Fashion series, that is second member. Okay. n2 is 6 in Passion series, that is third member. n2 is equals to infinity in Passion series, that is a limiting series, limiting members. So like this we have to call them. And in this case, substitute these values, then we get by doing simplification, then we get this one. And see, the wavelength value is increased in the Passion series. And next, it is the first member wavelength. Next, second member wavelength is C. For the second member, what is substituted in the place of n2? 5 only. So in the first member, in the place of n2 is 4, and the second member in the place of n2 is how much? 5. Okay. And substituting these values in the spectral term, then we get a wavelength value as this much. So it is a wavelength. And a limiting member means a n2 value, substitute n2 value as infinity. And then we get something by infinity is always 0. So 1 by 3 square means 9 only. So this is the term, substitute r value here, then you get wavelength this much. And this series where we see, it is also it is not in ultraviolet region. So I will explain later. So Balmer series and Passion series, we cannot see them in always in ultraviolet, infrared region only, and visible regions only. So I will tell you. So it is a mistaken. Next, bracket series. Bracket series is C. This series consists of all the wavelengths which are emitted when electronic jumps, where to where jumps from outer orbit to where? Fourth orbit. So see, fourth orbit. So from fifth to fourth, sixth to fourth, seventh to fourth, eighth to fourth, ninth to fourth, and infinity to fourth. So ending point is 4. So n1 is equals to 4 and n2 is equals to 5. Substitute, it is called a first member. See, substitute these values in this equation, then simplify them. So you can get this much value, and lambda values this is. Alright. And the next, second member. For the second member, second member n1 is fixed, but n2 value changes. In the previous first member it is how much? 5. It is second, in second member it is 6. It is for only passion, in for passion series only, right? And as of these values they here in the given equation. So see the wavelength value gradually increasing. Okay. And next, if you substitute n2 value as infinity, then what happens? That is called infinity is a limiting member. So then wavelength value is this one. So it is cannot seen in a ultraviolet region. So again I made one more ppt for this. I will show you in at the ending of this video. So at the ending of this video, all the series where they appear I kept in that one single table. So I will explain there. Next, after passion, now the after bracket, now the passion series, it is a bracket series. Now passion series, fund series. And see here in the fund series, electronic jump, where to where electronic jump takes place from outer orbits to ending point is fifth orbit. So different from the different level to last level is here fifth level. In the fifth level, if the electron jumping takes place, then they radiates different types of wavelength. All the wavelength can be found by using this formula. And see that formula. Now take n1 as fixed, it is a 5 for fund 5, and n2 is 6. Okay, substitute these two terms here. So why? Because 1 by lambda is, once again let me write, r into 1 by n1 square minus 1 by n2 square. So it is a formula. In this formula, if we substitute, then we get this is, and by doing this simplification by reciprocal, so lambda value is this, and finally wavelength value is this. Okay. Now next, second member. So for the second member, what? n2 value has to change, only n2 value, no need to change n1 value. So substitute in the following in this formula. So and doing simplifying this value, so we get this is. Okay. And limiting, for limiting what we have to do? n1 is fixed, n2 is infinity, then only it is called limiting member. Okay. So it is wrong, not ultraviolet. So by doing this by simplifying, substituting these values, then what we get? We get the wavelength value as this much only. Okay. And next see his table. Just now I said you Lyman series can be found, its position can be found where? In ultraviolet region. Lyman series n1 value, if it is 1, that is Lyman series. N1 value is 2, it is a Balmer series. N1 value is 3, that is a passion series. 4 bracket series. 5 fund series, right? And if it is n1 value is 1, always n2 value is greater than n1, right? n2 value is always greater than n1. n1 is greater than, sorry, n1 is less than n2. So n1 value is less always comparing with the n2, right? And suppose Lyman series ending point is this one, then energy, then electron jumping takes place where to where? From 2 to 1, 3 to 1, 4 to 1, so on infinity 1. For the bracket series, for the bracket, see here electronic jumping takes place from, it is ending point in the Balmer series. So jumping from 3 to 2, 4 to 2, 5 to 2, 6 to 2, 7 to 2, so on infinity to 2. So like this. For this, then the wavelength, they release the wavelength, and emitted wavelength can be found where? For Lyman series it is in ultraviolet. For Balmer series it is in visible region. For passion series it is in infrared. So and bracket is also infrared, and a fund is also infrared. So that means only Balmer series can be seen by us. Why? Because it is it appear in visible region, right? And ultraviolet, infrared cannot be seen by us. They can be seen with the other devices, but with the naked eye we cannot see directly it. we see directly only Balmer series, and a remaining series cannot be viewed directly. We can see them with some other materials, some other devices. So like this. And next to last one is what, Rydberg constant. Last one is Rydberg constant. Rydberg constant means in the following formula, see, we have written here R. What is this R? This R is a Rydberg constant, right? Its value is how much? 10.97 into 10 to the power 6 meter inverse. 6 meter inverse its value is, right? So like this. And a Rydberg constant, if you have to calculate Rydberg constant, so we have to substitute what, n1 value, n2 value, and a wavelength for particular term. For all the for different n1 and n2 and different wavelengths, we get our values always same. Okay, so that is what, this much only. So that is why it is called as constant. And n1, see condition here, n1 condition is n2 is always greater than n1. This condition is very very important condition, right? And with a different integral values of n1, we get different series. Yes, if it is n1 is equals to 1, that is Lyman series. N1 is equals to 2, that is a Balmer series. 3 Passion, 4 bracket, 5 Pfund series. So like this, these are the series. And thank you friends, I watch it this video till the end, then only you can understand it. But before watching, or if you want to understand all the wavelengths single, you must understand this table. If you know that this table, if you by heart this table, then no need to read remaining things. So you can easily get idea, and you can easily write the answer in the examination. So I hope you understand this one. Thank you friends. So again we'll meet again.